I don't like to bore you here. I'm a lot of experts in the field, a lot of companies outside, and we all know what is the typical application in the dental field, in the oral maxillofacial field, in the plastic surgery, reconstruction. But what are we doing currently in the field of 3D printing in our department? I'm the vice head of department, and let us start. I have only the 7 minutes. We are working a lot with orbital floor meshes, magnesium meshes, silicone prostheses, in the research, but even in the clinical field, the grinding splints. We all know this with typical problems at your joint. The dental people work with this, the personalized patient implants at the skull. We all know this. Let us start with a typical point. The idea was that we show our project was a EU grant, with the aim to ensure these patient care, customized implants. I'm always a big fan to show that we are working in a team. Without these guys, I had no chance of this. A lot of good engineers from the Fraunhofer. You can go to booth 11, you will see them. The Helmut Schmidt University for these artificial intelligence constructed implants, and the idea is always lower complication rate, less OR time, less time under anesthesia, a very quick workflow to satisfy these patients. And the first point in this grant was to get this database. It's not easy in the hospital with all these rules, to get these imaging data, then with an AI algorithm to get these data set, to print them. To print a patient-specific implant, it's not complicated. It's boring for you. We have 4 printers in our department. But the point was to avoid this typical process. Please give me 1 minute to explain. It's a short time. But the typical situation is, if you get a patient, you get a CT or a cone beam CT, a trauma patient or a tumor patient, and then to get a reconstruction, to get a patient-specific implants, to avoid any microvascular flaps, you have to upload these data. Then you did some planning appointment. Most cases in the morning, we are meeting every day, 7:30. Then we talk about these patients. We look on the CT data, and then we talk with the company. We have a collaboration with a company in the south of Germany. There are a lot of good companies in UK, in the US, all over the world. Then you have a delay of 3 till 5 days. This is the current workflow of the patient-specific implant without AI. That's the normal way since 15 years. After approval, the head of department, Professor Gosau, best wishes from him, I'm the vice head, or even the other senior consultants. When we make the okay, then we send this data to the company, and then it's fine. If there are any problems, you get a new planning. You even lose 1 to 3 days. Come on, guys, you will lose, you don't see this in the last line, you will lose 9 days in total to get a patient-specific implant for the patient. You know what I mean? 9 days. The patient is waiting, maybe in the internal area, and that's the big problem. Let us see, what was the idea with the AA? To get sustainability. I'm Dutch, I'm not the intelligent guy, but even Ralf Smeets understand at the moment in the world, everything is sustainability, No external partners to keep an in-house production. This is the idea of the guys in the university, in the UKA, in Hamburg, and we save costs, roundabout up to 50%. And we know at the moment, we save costs, we save time, we have a quality increase, the typical strategies of every company outside there, all over the world, in trauma surgery, in orthopedic surgery, and even in our field of head and neck surgery. This was the idea. We use the AI at the moment, and we can talk at booth 11 more in detail to get these better patient-specific implants. A patient-specific implants is nothing special. Scanning or CT or cone beam CT, the data and reprint. We now do this in-house, but AI-based. That's everything. A second project, if you give me this 1 minute to explain you, are the magnesium meshes. If you have a loss of bone, a trauma, a traffic bone, to insert implants, you have to do a bone augmentation. And the same strategy, my research is boring, scanning the mandible or maxilla, then get these data AI-based, and print them in-house, yeah? But now with magnesium. The typical strategy, you have a defect, the scanning, a algorithm, biolize the surface, and it's a magnesium meshes. Magnesium is a resorbable metal, yeah? It's an alkaline degradation with hydrogen expression, and then you have to put it out. In the past, we used titanium, and you put out this mesh, yeah? You will see later in our discussion that it works, in my opinion. It's always financed by the government. Yeah, thank you once again. Research is expensive. And the third point, in my opinion, my favorite, yeah, because at the end of the day, we had a lot of patients. Sorry guys, I put out all pictures which are bloody. I don't like to show you some bloody clinical pictures, but look on the left picture, yeah? You see some patients. We are plastic surgeons for the face, but at the end of the day, I'm MD and DMD, but first I study chemistry. And that's the reason why I'm always focused on surfaces, on some materials. And the problem is, these patients are mostly radiation. They have 60 gray, they have a chemotherapy, they have a bad vascularization, they have no regeneration, yeah? And then you have no chance with a flap. On the left patient, you see, we insert some implants in the orbital floor, in the bone, with some magnet, yeah? And then we produce some epithesis. In the past, 60 years, this technician do this. You know, technician like your crown, like your prosthesis, yeah? These are specialists for prosthesis. And now we print them, best wishes to Mr. Nguyen from the Fraunhofer, with silicone. And the idea was, look on the last sentence. The problem is, we have round about 10 to the point of 8 bacteria in our field, maxilla mandible. It's the most moist area of your human body, more than your stomach, more than your bowel. 10 to the point of 8. 1 milliliter sulcus fluid. Round about 700 to 900 bacteria. More than what you did on the toilet tomorrow morning. Yeah? Don't misunderstand. This is the most worst area in your human body. And then you insert there an implant. That's the difficult, infection of an implant. We loaded them antibacterial, and now it's the old boring idea with some photochromic and thermochromic properties. Yeah? The old idea, you know this from the tea cap, yeah? Hot tea, cold Coca-Cola, the change of the color. I first studied chemistry, we learned this thing to adaptive colorization, and if you have thermic difference, when we now go in the winter inside, you have a vascularization of your skin. The skin is red, but the prosthesis is still the same. In the past, the patient had 3-4 of these epitheses, very expensive. The government paid this patient, the tumor patient, they are boring patient, it's very hard for them, they pay 1 prosthesis. These patients couldn't go to the sun, to Ibiza or Mallorca, you know? You get coloring, but not the epithesis. And now we have this modification of this. The last minute, and then we finalize, yeah, this is the procedure. We print them, including these things, and at the end, finally, yeah, to close this session and then to present the better data from my brilliant guy, Mr. Gromzig. Yeah, we know we have a better surgical results with AI-based 3D printing. We have, in my opinion, reduced OR time, and at the moment, you know, 1 minute, it's around about 12, 13 euros all over the world. Without the MD, it's very expensive. To save OR time is the typical strategy. Cost savings, modern training, and even applicable for other inquiries, in my opinion. In academic teaching, in research, and in patient care. And at the end of the day, I have to say thank you. I can talk a lot here. I'm not important. The team is very important. And I say thank you to the DFG. I have a Heisenberg professorship of the DVG for regeneration. Thank you very much for this. This is the team for the 3D printing, brilliant guys from the Fraunhofer. I say thank you for the AI support from Professor Niggemann, and I say thank you to you. Best wishes, take care of you, keep healthy, and a wonderful Christmas. Thank you very much. Thank you.
On with my presentation, AA by 3D printing strategies for patient-specific implants. And Ralf has talked about the reconstruction of orbital floor meshes or orbital floor fractures in general, and I will go more deep inside and show the technical solutions which we have found in the project. So the project was DigiMe, digital and physical workflow for additive manufacturing of patient-specific implants. You see the holistic workflow there, split it into the digital and the physical workflow, and you all know this. We have the medical imaging at the first step, data acquisition, CT, MRT data, DVT data. Next step will be the reconstruction model of the fracture, so that we have a digital reconstruction at the first site, and then we have derived the implant design generation, so that we have at the end a digital version of the physical implant at the end. When we look at the physical workflow, we start with the additive manufacturing there. In the project, we use the LPBF technology and titanium alloy. And in the next step, the post-processing steps, we have more or less automated it. So it's a bit manual work. When you look at the support structures, they have to be removed manual. But the surface finishing in the post-processing step is automated. And at the end, we have the patient-specific implant, which is sterilized and can be handed over to doctors in the hospital. So, and the holistic process chain is underlined with the MBR compliant quality assurance concept, which we have defined in the project. When we look more to the pre-process, we have an AI-based reconstruction and design, and you can see the different steps. At the first one, we have an AI algorithm for the segmentation. So here we use a convolutional neural network. In the second step, we have the virtual reconstruction using a statistical shape model, and at the end of the pre-processing in the digital workflow, we generated the implant using a second AI algorithm, and then we can hand over the digital version of the implant to the physical workflow and print them. When we step in the in-process, we have concentrated on the digitalized quality assurance. This was the main step there. And yeah, you see the goals are the increased trust in data, the efficient in internal and external collaboration, the stability of processes and systems in this case, and moreover, reduce cost and effort and time. So the approach was to develop a Q&A database, and where we can import the process data and metadata. See there on the right side, this could be the volume, build height, process parameters as well. On the other side, laboratory data, tensile test, powder data, and so on. And I've talked about it a bit before. When we look at the post-processing, we have make an approach to automate it. You see here a sandblasting system, which is CNC based, and we have from the pre-process the CAD data of the final implant geometry, and we can then calculate the automated path calculation for the implant and derive in the next step a G-code so that it can automate sandblast with the CNC system. So these are the pre, in, and post-processing steps we have optimized or new developed. And now I will close my talk with MDR compliant quality assurance. I've said it before, we have developed an approach of a certification concept along the whole process chain, so physical and before the digital. And the requirements were here belong to the MDR requirements, which we have, then the confirmation certification by an accredited testing authority, which is very important, and at the last step, when we want to integrate it in the clinical environment, we have to do it in this way that we can integrate it in a easy way in the clinic. So the approach was to develop an overall certification concept. You see here the presentation of each sub-process in the flowchart on the right-hand side, and we have to identify and standards and quality assurance parameters, and define active processes as specifications and verification processes. In the next step, we have elaborated the flowcharts for each single step in the digital and physical process. So imaging, AI-based reconstruction, and implant design are the digital processes, and in-process, adaptive AM process, and automated post-processing, and digital quality assurance are the physical processes moreover. And last, the generation of default and verification documents for each single step there, so that we have work instructions, documents for education, constructions and evaluations for AI, generated implant design, and the validation of PSI data set by the engineer and the doctors together. Yeah, last, I would thank you, the team from the UKE, HSU, and from our side, the IAPT, and special thanks to the IFB Hamburg. This was a project funded by the European Regional Development Fund. And yeah, thank you for listening. And